Lesson 1. Probability terminology and notation. Probability theory deals with the mathematics of chance or prediction. The following terminology will be used. A trial is any operation whose outcome cannot be predicted with certainty. For example, we can toss a coin or we can roll a die. An experiment consists of one or more trials. We could roll one coin. We could flip two coins. We could roll two dice. We could flip a coin and roll a dice. An outcome is the result of carrying out an experiment. So if we flip a coin, we could get heads. If we roll two dice, we could get a 6 and a 4. If we flip a coin and roll a die, we could get tails and a 4. The sample space of an experiment is the set of all possible outcomes. So for flipping a coin, we could get heads or tails. Rolling two dice, we could get 1, 1. We could get 3, 4. We could get 6, 6. The list of all these possible outcomes are on your formula sheet. If we flip a coin and roll a dice, we could get heads and a 1. We could get heads and a 5. We could get tails and a 2. And we could get tails and a 6. An event is a subset of the sample space. It consists of one or more of the possible outcomes. To denote the probability of an event A, we write the probability of A. Probabilities are usually represented by decimals or fractions between 0 and 1, but sometimes percentages are used. For any event A, the probability of A will fall between 0 and 1. If the event X does not include any of the outcomes in the sample space, then the event X is impossible, and we would write the probability of X equals 0. For example, the probability of rolling a 9 on a standard die equals 0. If the event Y includes all of the outcomes in the sample space, then the event Y is a certainty, and the probability of Y equals 1. For example, the probability of rolling a natural number less than 7 on a standard die would be 1. If an experiment has a set of equally likely possible outcomes, then the probability of a particular event A is given by the formula. The probability of A is equal to the number of outcomes favorable to A all over the total number of possible outcomes, which is also the sample space. For example, the probability of rolling a heads when flipping a coin would be 1, because there's only one way to get a head, and it would be over 2 because we have a sample space of 2 heads or tails. Example 1. Consider these two examples. A. A fair die is rolled. What is the probability of rolling a 1? Note here that the outcomes would be equally likely. You would just as likely roll a 3 as you would a 4 as you would a 1. So the probability of rolling a 1 would be 1 over 6, where 1, the favorable outcome, which would be just the 1, and 6 being the sample space, because you do have the possibility of rolling a 1, 2, 3, 4, 5, or 6. B. Using the following spinner, which is divided into 4 equal sectors, what is the probability that it lands on a $5? Again here, the outcomes would be equally likely. Each of those sectors are the same size. So the probability of the spinner landing on the $5 would be 1 over 4. 1, because the 5 is just one of the 4 possibilities, and the sample space on the bottom 4, because there are the 4 different possibilities that we do have. Complementary events. When the spinner in the example above is spun, The sample space consists of the four outcomes, 0, 5, 10, and $20. The event lands on $5 consists of one outcome and has a probability of 1/4. The event does not land on $5 consists of the three outcomes, 0, 10, and $20, and has a probability of 3/4. The event does not land on $5 is called the complement of lands on $5. The events lands of $5 and does not land on $5 are called complementary events. The probability of an event and the probability of the complement will always add to 1. So the probability of A plus the probability of A prime equals 1. The complement of an event A is the set of outcomes in the sample space that are not included in the outcome of event A. The complement of A is denoted as A prime, and the union of the set of outcomes for A and the set of outcomes for the complement of A will be all the elements of the sample space. Compound events. Events formed from repeated trials or from a combination of simple events are called compound events, and often a table, a chart, or a tree diagram is useful in determining the sample space. Consider, 2 coins are tossed and the number of heads is counted. What is the probability of obtaining 2 heads? We can list the sample space as 2 tails, 1 head and 1 tail, 2 heads, and the favorable outcomes as 2 tails. Since there are 3 elements in the sample space and only one of these is favorable, would the probability be 1/3? Well, outcomes are not equally likely, so no. We can show this with a tree diagram, as seen below, or as a table, also shown. Now we can see that our sample space is actually 4. So now we know the probability of obtaining 2 heads is actually 1/4, or 1/4. Determine the probability of 2 tails. Also 1/4. The probability of 1 head and 1 tail, we now have 2 ways of getting that. So it would be 2/4, which is also equal to 1/2. Example 2. What is the probability that in a family of 3 children there are exactly 2 girls? We're going to first draw a tree diagram to represent the possible arrangements of the boys and the girls in the family of 3. Now we do have to assume that each possibility is equally likely. So the probability of a girl is 1/2 and the probability of a boy is 1/2. So in our tree diagram we start with our first child. We have the option of having a boy or a girl. With our second child, we now have 2 children and we can have boy boy, boy girl, girl boy, or girl girl. Then we look at the third child. So under each of those options that we have so far, we now have the option of a boy or a girl for our third child. So first we want to determine the number of branches that contain 2 girls. So if we notice the branch boy, girl, girl has 2 girls, the branch of girl, boy, girl, and the branch of girl, girl, boy. So we have 3 possible branches. Now, we have 8 total outcomes in this arrangement, so our final probability would be 3/8. I'm now going to show an example where we're going to use a table. So we're going to go back to the spinner question that we used before, and when the pointer is spun twice, we're going to find the probability that we win a total of $10. So I've got our first spin along the top, I have our second spin down the left, And in each box we're going to do the sum of the two. And as you can see, $10 occurs 3 times. So here, out of the possible 16 combinations, 3 will give us $10. So our probability of winning $10 will be 3 out of 16. For part B, I just want to show how we can set up the table just slightly different. Instead of doing the sum of the two spins, I'm going to leave them separate. So now my table is going to be filled in with ordered pairs, with the spin from the top row first, followed by the spin from the row on the left. So we are now looking for the two spins that give us the same numbers. So here we can see it's 0, 0, 5, 5, 10, 10, and 20, 20. So out of the possible 16 combinations, 4 will give us the same number. So the probability of the same number is 4 out of 16, which can be reduced to 1/4. Our last concept is experimental probability. For the most part, I really just want to make sure that you understand the difference between the theoretical probability and experimental probability. So we're going to start by visualizing rolling a die. And we want to know what the theoretical probability of getting a 5. Well, that's what we've been working out up until now. 5 is 1 out of 6. But if we were to simulate rolling a die 300 times, and we recorded the number of times that the 5 appears, it would not necessarily occur 1 out of 6 times. The experiment will be slightly off. So our experimental probability will be the number of favorable outcomes from an experiment divided by the total number of the outcomes. So if we did that 300 and we rolled a 5 55 times, our experimental probability would be 55 over 300. We would get a slightly different answer each time we did that experiment. For example 4, let's say we flip a fair coin 200 times and it comes up heads 110 times. What is the experimental probability of flipping a tail? Well, we know the theoretical probability would be 1/2. Now, because in the question it says 110 times that we flipped a head, we want to know for tails. So we do the subtraction, 200 minus 110. So we flipped a tail 90 times. So our experimental probability would be 90 over 200, and we could reduce that to 9 over 20.